All right. So thank you so much, everybody, for attending Keelan's and my talk today about this big user study that we did comparing time, accuracy, satisfaction, and accomplishment in VR versus desktop implementation of the RUI, the one and only RUI. Thanks so much for attending. Um, just one word in advance. This is one user study that we did, but there is another study where we talk about optimizing these completion times and the accuracy. That is going to be a different, maybe a different talk at some point in the future. So the subjects that we talk about here today are the control cohort of the much bigger user study. This other user study that we do not cover today, but that we also collected all the data for, is about testing VR visualizations to allow an experiment cohort to improve their performance in the second phase of the tasks. So now we're going to show the results only from analyzing the control cohort. And then during Q&A, if there is any time, we can give you preview about the results of that bigger study. So let's get into the meat of the matter. We're going to talk about registering human tissue blocks. And just a little warning, there's going to be some graphical images of a human kidney coming ahead, although I assume most of you have seen those by now. So the RUI is part of HubMap by NIH, which is with the stated goal of creating a Google Maps of the human body in incredible detail. You can see that here on the right side. So our lab contributes the registration UI, or RUI. Version 1.0 was deployed just recently in October 2020 after about 1.5 years of prototyping and development. It is used by labs across the country to generate metadata for downstream use in HubMap. To give you an idea of the physicality of this registration, this is how registration is commonly done in labs. So you have these either entire kidneys, like you see here at the top, or you have bisected kidneys or just tissue blocks like here, and they are just being put on these cutout boards with metric numerical scales, and then these photos are being taken. And so the RUI works on digitizing this kind of step. So here on the bottom left, you see a registration step for the human kidney, in this case, the male left kidney. And then on the right side, you're going to see a bisected kidney. And so if you wanted to register a piece from down here in the kidney, it would look something like this if we replicated that in the RUI. So the question that we ask in this research is, how does a VR interface compare to a desktop interface for object manipulation? Obviously, the RUI that we deployed is a desktop interface that runs on a 2D screen deployed via the web. So let's talk about the user study design that we have. But let's first talk about the research questions. So research question number one is about performance, accomplishment, and satisfaction. So how do the input devices, such as the keyboard, mouse, and the VR controllers, influence the task completion time, the accuracy, and the user satisfaction for these manipulations for the RUI on a laptop and on tethered and tracked VR? Okay. Research question number two is about the trade-off between accuracy and completion time. So for each of these three conditions that we are testing, what is the trade-off between these two performance metrics? So is there a point at which time investment does not yield a higher accuracy over time? Research question number three is about the relationship between the task complexity and the task completion time. So do tasks, as they get more complex, automatically take more time? Research question number four, we talk about plateau levels. So in this case, we present users with a sequence of 30 identical tasks, okay, 30 identical tasks in what we call the plateau phase. We're going to talk about that in a second. And so can we observe a flattening of the learning curve when we plot the completion time and other performance metrics over the amount of trials? So at what trial does the user achieve a maximum throughput? And how long does it take for these three conditions to get to this kind of plateau level? Research question five is just for the VR conditions. It's about the usage of 3D space. So are there different usage patterns of physical space? We came up with a little metric there to describe this. And then what is the effect of this usage pattern of the physical space onto the performance metrics? And then lastly, we look at the button usage. So all three conditions give the subject the opportunity to reset the position and the rotation of the tissue slices or the tissue blocks that they have to register. And so we want to see what is the difference in reset button usage. We did formulate some hypotheses, and Keelan is going to go over these one by one later as we as we actually get to the point where we talk about the results. So I'm not going to go too much into detail here, but as you can see, these correspond to the research questions that we formulated before. All right. Now it is time to talk about the user study design in more depth. So again, I mentioned earlier that we have 3 conditions. We have stand-up, tabletop, and desktop. Okay. And you can also see these 3 here on the side. So VR stand-up, the user is in VR. They stand as they match these 2 cubes. In tabletop, they sit at a table. In fact, a physical table that is replicated here in VR, and the kidney just kind of floats here on the left side, and they do the match up here. And then here, this is the desktop version that is modeled after the prototype version of the RUI. You can see how the same registration is being done. We had 42 subjects with a pre and post questionnaire, as well as a series of tasks. So they had to match a tissue block and a target block. You see the tissue block here in white, and the purple is the target block. And they have to match these in position and rotation, all while being timed. Okay. So this is a little flowchart showing how we designed these tasks over time. So we have the pre and post questionnaire at the beginning and at the end. Then we have a tutorial task. That is just one task where the user listens to an audio explanation of the interface, and it's kind of an introduction to the whole thing. Then we have a ramp up phase. Those are 14 tasks total that get harder over time. So the tissue and target blocks get smaller and smaller. You can see they're pretty big here, and then they're pretty small here. The distance becomes bigger and bigger over time, and the rotation becomes harder and harder over time as well. And then lastly, we have the plateau phase here, where we have 30 identical tasks with about medium distance and medium size, but maximum rotational difference. How did we normalize the difficulty of these tasks relatively across the conditions? So you see this table here. On the left side, we see the 3 phases: tutorial, ramp up, and plateau. You can see the task numbers here. And then here we have the scale of the tissue blocks and the target block. They're always the same size. So at the beginning, both of them in tutorial phase are 0.2 times the height of the kidney. K is the height of the kidney. Okay. So the height of the kidney is really what we use to make sure that we increase the difficulty inside all of these conditions in an equal manner. And then we use some unity magic to basically interpolate the size of these 2 blocks over time. So at the end, they are 0.05 K, so 5% the height of the kidney at the end, okay? And we set this value by where we are in the whole task sequence. We can see it just gets harder and harder over time. The same goes for distance. Initially, they're just 0.3 K away from each other. And then at the end, they end up being 2 K away from each other, so twice the height of the kidney. And then rotational difference works a little bit differently, just because rotation works differently from these more linear values. We also use some unity magic to interpolate between 2 rotations. One is a 0 rotation, so no difference between the 2. The other one is a 180-degree diametrically opposite rotation. In addition, we give speed and accuracy prompts. So as we did user testing or the pilot study in the beginning, we noticed that many users would completely bog down in accuracy and trying to achieve an accuracy level that was not possible. So we tried to ameliorate that by adding these different prompts for speed and accuracy. All right. So let's again look at what a task is. The idea is to match a tissue block here in white with a target block here in purple. You can see a VR stand-up user doing that here. That's how this worked. And we're using RGB spaghetti poles for rotation, just because there are 6 different combinations when you match 2 cubes in rotation that would theoretically be correct. But in order to make sure there's only one possible solution, we added these poles. And we're going to represent rotations with these arrows for the rest of the talk. Now let's again have a closer look at the conditions. On the left side, we have our desktop interface with mouse and keyboard, actually just with the mouse. In the middle, we have VR stand-up. You can see the user stands and moves the tissue block around. And then you can see VR tabletop here where the user sits. And another interesting bit is that the user can actually rotate the kidney with a press of a button as well. You can see that here in a second. The kidney rotates. The users indicate themselves when they want to move on. So in VR, they have this little buzzer button. It's like a little red button that you're going to see the user press here in a second. Very physical feeling. And then the desktop is just the next button. We also have reset functionality. So here we can see a user resetting first the position and then the rotation of a block when they feel like they messed up so much they just had to reset everything. And then here in desktop, we have these little circular arrow buttons that allow us to reset the position and the rotation separately. How do we measure accuracy? There are really two metrics for that. One is the distance. Distance is fairly straightforward. Distance is just the difference in position between the centroids of these two blocks. Of course, this distance is just a single float value. And then the rotational difference is a angle from 0 to 180 degrees. Rotation is a lot more complex than distance, like the three-dimensional positions that make up that make up distances. So we use some Unity magic that gives us a singular rotation value between two rotations that allow us to more easily compare these with each other. So let's talk a little bit more about the increasing in difficulty. On the left side, we see task 0. That's the tutorial. We can see the scale is 0.2K, so about 0.2 times the height of the kidney, and the distance is about 0.3K. Okay. And then here in task 12, that's a late ramp up phase task, where we see that the scale is significantly smaller and the distance is significantly larger as well. And then in the plateau, here we can also see, it's kind of hard to see here, so I added these. This is the exact same orientation. And here the orientations are almost exactly opposite of each other. That was an essential part in making these tasks harder over time. And now we have the plateau phase. Again, these are 30 individual tasks where the scale is always 12.5% of the kidney height and 1.15 times the kidney distance. 1.15 times. All right, and the rotation here is always diametrically opposite of each other. All right, with that, I want to give it over to Kilian, and he's going to present to us the results.
Okay, first, some summary statistics. So for every subject, every one of the 42 subjects, we recorded 44 different observations, 44 different tasks, 14 for the complexity phase, and 30 for the plateau phase. That totals in 1,848 data points, 616 for each condition. We have what we call the performance metrics, the completion time, the centroid inaccuracy, so it's the centroid distance, and the rotation inaccuracy, that is the distance in rotation. If we look at the means for each of those metrics, for each of the conditions, we see that in the VR conditions, stand-up and tabletop, the means are significantly lower than for desktop. That is true for completion time, for centroid inaccuracy, and for rotation inaccuracy. We also recorded a Likert type scale data for the feeling of being accomplished after the whole experiment, and the feeling of satisfaction. We have 42 observations, one for each subject from the post-questionnaire. Also, we tried to control for previous VR experience and experience with 3D interfaces, for example, video games, first-person shooters, 3D modeling software, and the usage of VR hardware. Next slide, please. In the first research question, we tried to look at the different performance measures for all the different conditions. If we look at plot A in the upper left, we see the mean time needed to complete a task for the complexity phase, in the complexity phase for all of the conditions. On the x-axis, in all the plots, there are the conditions. On the y-axis, it's always the performance metric. We see that the mean time to complete a task is significantly higher for desktop users than it is for VR users that do not differ from each other. If we look at plot B, we see this is also the case for all the single tasks. So not the average time needed for the tasks, but every single completion time. Plot C shows the centroid inaccuracy for all the tasks of all the users across all conditions. This is a bit harder to decipher because of the many outliers in the desktop condition. But the pairwise Kruskal-Wallis test with alpha inflation correction that we did for all the distribution analysis here shows us that the desktop condition again differs significantly from the VR conditions that also do not differ from each other. The same is true in plot D for rotation inaccuracy. Again, desktop subjects performed worse. Plot E and F in the bottom show us the feeling of accomplishment and satisfaction. In plot E, we see that the distributions for the feeling of accomplishment in the VR conditions does not differ much. And even though in the desktop condition, the median is lower than in the VR conditions, there is no statistical different distribution here. In plot F, we see a significantly different feeling of satisfaction for desktop users. So this is how all the performance measures differ across conditions. Next slide, please. Then we looked at whether there is a trade-off between the time a user takes to complete a task and the accuracy, the centroid inaccuracy and rotation inaccuracy that is achieved. Here we see two scatter plots for the stand-up condition. And since we asked every subject to focus either on completing the task as fast as possible or as accurate as possible, we can control for that. We did a correlation analysis, and we see in the left plot that there is a significantly negative correlation between completion time and centroid inaccuracy. So there is a trade-off. People that take more time are able to place the tissue more accurately. This is also the case in the right plot. Subjects in stand-up condition that take more time are able to place the rotation more accurately. In the next slide, we see the tabletop condition. Here, the results are already different. While there is a significantly negative correlation for centroid inaccuracy, we do not see that trade-off anymore for rotation inaccuracy. So for rotation inaccuracy, the data shows that there's no trade-off between completion time and inaccuracy. And last but not least, in the desktop condition, we also do not see any significant correlation between completion time and the inaccuracy measures. So this is somewhat interesting. We hypothesized that there will be no trade-off, so that since users won't be able after a certain amount of time to be more accurate, that there won't be a trade-off. But there is a trade-off for, we see that in the next slide where all the plots are shown. There is a trade-off in the stand-up condition, but, and this is mostly the case for the desktop condition, the desktop condition is completely robust against effects like that. Even if we tell the subjects to focus on accuracy, they do not become significantly slower. And if we tell them to focus on speed, they do not become more inaccurate. So we have to reject hypothesis 2. Our next research question concerned the relation between task difficulty and the performance measures. So, as Andreas has told you, the complexity tasks become more complex with every task. The rotation becomes bigger, the tissue slices become smaller, and the distance between the spawning point of the tissue slices and the target become further away. Since all those differences between the tasks are equally spaced, we can just look at the correlation between task number and the performance metric. In the table, you can see those correlations. In the left column, we see the correlation between task complexity and completion time. There we see a positive correlation for all the conditions, but for stand-up and tabletop condition, this correlation is not significantly different from 0. In the desktop condition, we have a positive correlation, so if the tasks become more complex, the subjects need more time to complete those, and this is significant to the 5% level. In the middle column, we see the correlations for task complexity and centroid inaccuracy. Those are all not significantly different from 0. And for rotation inaccuracy, we can see that there is always a significant positive correlation between task complexity and inaccuracy. So the more complex the tasks get, the less accurate the subjects get in rotation placement. Next slide, please. So now we come to the plateau tasks. In the plateau tasks, we wanted to check whether the subjects have a learning curve and when they reach a learning plateau. That learning plateau is defined as the point where the variation in the performance does not reaches a steady level, stabilizes at a certain plateau. We check this with computing the relative deviation from the mean for each subject, and we do not primarily look at what level this plateau is, just whether a plateau is reached. That can be high or low individually. In the plots on the right, we see the data from a sample subject. In plot A, we see the relative deviation from the mean time for all the 30 plateau tasks that are on the x-axis. And we see that there's a high deviation from the mean in the beginning, but at task 4 and after task 4, the deviation starts to stabilize. So the plateau is reached at task 4. In plot B, we see the relative deviation from the mean centroid inaccuracy over time, and the plateau is reached very early at task 2. And in C, we see the relative deviation from mean rotation inaccuracy over time, and the subject reaches its plateau fairly late at task 11, but after then stabilizes. In the next slide, we see the distributions of when the subjects in stand-up condition, tabletop condition, and desktop condition stabilize after how many tasks. And we see that in plot A, in the VR condition, the subjects stabilize very early in terms of time needed, and desktop users stabilize later. But for the accuracy measures, centroid inaccuracy and rotation inaccuracy, we see that there is no significant difference in the task number at which the subjects stabilize their performance. So there's no significant difference. On the next slide, we see at what level they stabilize, and this paints a different picture. even though in plot B and C, we saw that there is no significant difference at when the subjects stabilize, but we see that there is a significant difference, at least for centroid inaccuracy, at what level they stabilize. This is also true for completion time. Again, desktop users take more time and have a lower centroid inaccuracy, even at their plateau phase. In plot C, and this is interesting, the distribution is not significantly different from the VR conditions. This might be because of the different sliders that can be used for the rotation that can be memorized by the subjects. So that there we see no significant difference between desktop and VR. Then we looked at how the space is used in VR, in the VR conditions. For each user, we tracked the position of the right hand or the right controller, the left hand controller, and the head in space. We used two different metrics for the space usage. First, the convex hull, that gives us an idea about what amount of space was used, but doesn't tell us anything about the concentration of where the user operated in space, just the raw amount. For the concentration, we computed the optimal number of clusters in k-means clustering. So we had users that operated from a lot of clusters, that changed their location often, and also users that kept operating from a single point, that have very few clusters. We constructed the metric space usage, that is just the convex hull times the number of clusters. So a user that has a large space usage moved around a lot in space and operated from different points. And users that have a low space usage obviously did not take up that much space and operated from very few points. It comes as no surprise that stand-up condition users took up more space for the head, the left hand, the right hand, and overall, just because they can move around freely in their virtual space, whereas the tabletop users were sitting at a desk, so they didn't have the chance to move around as much. But we can see on the next slide exactly how this correlates with performance and accomplishment and satisfaction. This is a correlation matrix. The blank spaces are insignificant correlations, so they are not shown, and the correlations that are shown are all significant to the 5% level. We see that space usage in the left column is positively correlated to the feeling of accomplishment in the stand-up condition. It's not correlated with completion time, and it's not correlated with rotation inaccuracy, but it's positively correlated with centroid inaccuracies. So people or subjects that move around a lot also tend to have a higher inaccuracy, a lower accuracy when completing their tasks on average. If we look at the tabletop condition, the results are completely different, also because the setting is totally different in terms of space usage. Subjects that move around a lot do not feel accomplished anymore, but they feel more successful, and they take more time. There's a positive correlation between the time taken per task and the right-hand space usage. And last but not least, we look at the button usage, about the reset, on the reset button usage for rotation reset and for location reset. We see in plot A that desktop users make use of the rotation reset button significantly more often than VR users, even though there is a very interesting outlier in the stand-up condition that used the rotation reset button 19 times. In plot B, we see the use of the position reset button. There, the standard condition has the lowest button usage and differs significantly from tabletop and desktop, which do not differ from each other, statistically speaking. But Andreas informed me that he looked at the videos that were recorded from the subjects, and those were actually, for the tabletop condition, all accidental button presses. And if we combine both numbers and look at the subjects that used any reset button, position reset and rotation reset, we see, and this is also no surprise, that desktop users made more use of any reset buttons significantly more often than VR users. Those are the results.
Thanks, Kilian. All right. We're going to go into a brief discussion segment, and then we're going to have an extended Q&A because we are really curious about feedback from the audience about the results and about the user study methodology. So as we saw from the results, is that desktop overall is less accurate overall. But, and that is a big but, and that's important to mention here in this discussion and in the paper, the RUI in the desktop version is cheaper and easier to deploy. And that's very important for adaptation of this real world interface. Furthermore, the high level of position and rotation accuracy that we tested for might not be needed in real world usage, where oftentimes our users have very, very limited understanding of where exactly the tissue comes from inside the organ, and where much of it is built on guesswork. Whereas we were testing for an extremely high level of accuracy, where we gave the user a precise target to match the tissue block to. Of course, the RUI in the real world also is used for fine registration, and fine tuning happens later in separate applications. For example, the R2 UI that our lab is also developing. Now, stakeholders of the actual interface so far had no issues using it at all. In fact, you see on the bottom left, you see a screenshot of Leonard working with the team at Vanderbilt to actually register human tissue slices, human tissue blocks for the kidney. And these stakeholders do not need this level of accuracy. So VR is better for fine accuracy, but of course it is also way more expensive and time consuming to use. And it is simply not as common yet. You cannot expect a lab to have a VR setup or even be able to use one, like having the expertise to use one, which of course has been an issue with VR setups for a long time. And so what you see here on the right side now, these are actual tissue blocks registered with the RUI. So you can see all of these tissue samples here in the kidneys. Those have actually been registered. Those are actual samples registered with either the prototype RUI or going forward, the new RUI version 1.0. Now, what are the design implications for the RUI 1.0, like the one that we just pushed out and the one that we are going to continue to develop? There are several things that we can do to support what our user does, since we know that it is not optimal for high accuracy registrations. The first thing that we added that is really useful to keep supporting our common extraction sites, adding as many visual guides as we can to make sure the user knows where they are going inside this organ. Furthermore, the anatomical structure tags, enriching the metadata that the user generates, from something that's, simply geometric to something that's a little more semantic with the addition of these anatomical structure tags as the user registers their tissue block into the organ. Another thing that we may want to consider at some point is to rethink the slider approach and to go to something that's more direct, something like handles around the 3D object, like it's common in 3D modeling software. Alternatively, we could think about adding a text input. So as you remember earlier in the Plateau phase, users were surprisingly good in the desktop condition when they had to make repeated adjustments about the same rotation. So adding maybe a text input field would help users make repeated registrations more easily. But of course, this is a pretty big conversation and a pretty big design implication. Because as we saw, rotation and accuracy was one of the biggest issues by far for the desktop condition. There are, of course, also essential features that we did not test in the study, and I have to really emphasize how important that is. For example, the RUI has a pretty intricate stage management. So we have a metadata pane on the left, a 3D stage in the middle, and a 3D adjustment pane on the right. There was no metadata pane like this in the RUI that we tested, because it didn't exist in the RUI prototype. It was outsourced to a separate page, and it was also not necessary for the study. And this is really important, because if we wanted to have panes like this that allow for the user to do the whole registration within one interface, this would be very hard to implement in VR. If you've ever used an interface that was clearly developed for 2D in VR with checkboxes, etc., it is much more tedious to use than it is on a 2D screen with a mouse. So this is something where clearly the 2D interface is superior. And of course, we did not, again, this is not something that was part of the user study. And these three stages are very important for data provenance, indicating where the data comes from. And of course, we also can actually export the metadata here. And because the RUI is running in a web browser, it integrates seamlessly into all the other applications that a user would do on a laptop. If you put a user into VR and you let them do the registration there, it has to be some kind of a handoff between the VR environment and the desktop environment. And there are currently no good solutions for this. There is no integrated VR desktop environment where you can perform a task that is spatial and that happens in VR or in 3D, and then transitioning to something that is happening on the screen. It just doesn't exist yet. And even so, it would be a long process for our stakeholders to adapt to this kind of environment. All right. We are at the end of the content. We have plenty more in stock if people ask about it. But for now, we would just love to hear your questions. And I see that Kadi has already posted a plethora of questions into the chat. Kadi, is there maybe one question that you would find particularly important?
First of all, those are for both of you and also in support of the paper. So you don't have to answer them all now. The most recent answer, I think, is relevant. So in the setup, you have different sizes of the kidney in VR and also in desktop. And then you have the tissue blocks. And I'm curious to understand, what is the accuracy in real world millimeter? And maybe it's 0.1 for VR and something else for desktop, but have you had a chance to compute that?
Yes, there is. I'm going to go to that slide, Kilian, where we talk about the here, the plateau level.
And I know you have it in the virtual world, but I want to hear it in relationship back to the real world.
Okay, so Kilian, if you want, you can just jump in. So I went to this slide because here we actually see the centroid and accuracy plateau levels. So in VR, if you read these values, this is below 1 millimeter. Okay, so this is in meters. So this is below 1 millimeter. And so in the 3D context of the desktop scene, we are just under 6 millimeters. Now, what does that mean? It means that if we translated what we have on the 2D screen and desktop into a 3D world, it would be just below 6 millimeters. And I have to emphasize that this is theoretically an accuracy that is way higher than anything that the RUI could reasonably support. Again, we have to remember that in the real world, the RUI, mostly there exist photos with some very, very rough idea of where the tissue slice is coming from. And so aiming for an accuracy that is higher than that seems unrealistic to me. Kilian, do you want to weigh in on that as well?
Yeah, I think it's the accuracy in desktop is much higher than in VR, but this is also a condition where there is a clear target where to put the slice. Mm-hmm. That does not exist in the real world. The people registering the slices do not have a target like this. They have information about where the sample comes from, and place it roughly at that position. And I think 6 millimeters is good for that.
And to follow up on that also, we just talked about the centroid inaccuracy. Let's talk about the rotation inaccuracy as well, which presented the bigger problem for the most part. Again, the users had a clear target with 3 RGB spaghetti poles that they had to imitate exactly. If you take an actual cuboid, like if you take an actual like same-sided cube, there are 6 different combinations to arrive at the same rotation. Later in the RUI, when people register the rotation of the tissue slice, the exact rotation does not matter all that much because there are many different combinations to get to the same rotation, and the rotation is going to look the same when you show it in the EUI later. So this is again a level of accuracy that we were testing here for that is not applicable in the real world.
So can I ask one more time? So you mentioned this is the middle B plot is in meters. So if it's in meters and it's 0.06, then it's 6 centimeter.
Oh, yes. Apologies for that. So we are below 1 centimeter.
The entire kidney is 10 centimeter, right? And it's not going to make plus. So I'm still wondering.
Kilian, can you clarify the y-axis labels?
Those are the y-axis labels from the data. I do not exactly know how the scene units in the environment are translated to actual real-world metric measures. That is something you must answer.
Yeah, I think we can find it out via, we know how tall that kidney is and how tall it is in Unity and how tall it is in the real world. So I think we can get there. So I would love to have that number because this is an important number and we might like to have that also in the paper. In general, I mean, this is great. I love the talk. Thanks so much for all this work you did here. A really great presentation also and so much detail and a lot more data than I ever expected. So thank you for that. But we also have Josh here on the call, and I think he will, for him, plus minus 1 millimeter is a huge difference from plus minus, let's say 2 millimeter, because he has to do that movement pixel by pixel, you know, rastering everything in 2D. It's just a huge different, a very different kind of computing time that he would need to manage one versus the other. So it will be interesting to learn this number. And Josh, I don't think you need to give up. I think there's hope, but I would love to have that number.
So something that we can do, Kadi, is Yash and I can go into Unity and we can have a look at the RUI and we can take measurements there. Now, of course, Bruce basically had to rebuild everything that we did in Unity with DeckGL, but commonly in 3D software, the scene unit is in meters. So what that means is when you download any model from Sketchfab or any other repository, they are always modeled in meters. So that if I import, for example, a model of Laddie Hall into Unity, it is exactly 20 meters tall, 80 meters wide, so that it scales up correctly. Now, of course, if you're in VR, you go in there at a 1:1 scale. So the kidney there is actually 60 centimeters tall, which is large. I mean, that's like 1/3 my own body height. If you do the same thing on a 2D screen, the scale might be completely off. And then maybe scene units is not the best way of communicating how tall the kidney there is.
We should maybe put this rotation, the centroid inaccuracy relative to kidney height.
Yeah.
Okay.
Yeah, we can discuss this. So let's see if there are other questions. I don't want to dominate this, but this is great work. Thank you.
I also know that it was a lot of data that we presented here.
Yeah.
It was interesting to me. You're showing how the difference between user satisfaction in each of the conditions. And then when you mentioned that maybe the accuracy that you're asking for in both position and rotation might be above and beyond what is needed, it might improve the satisfaction of the desktop users if they're not trying to get it exactly right. If there's a little more wiggle room as far as accuracy, they may actually have a more pleasant experience with that than the VR users.
Speaking on that, I'm bringing up a slide that we decided to talk about if needed. So one interesting thing that we see here in the desktop condition, we have a negative correlation. So this matrix here shows the influence of the inaccuracy in the desktop condition on the feeling of accomplishment. And we can see that inaccuracy never has an influence. Like inaccuracy has no influence on the feeling of satisfaction or accomplishment in any of the conditions other than the desktop condition. So what this means is, the higher the inaccuracies, the lower the feeling of accomplishment. And so there's also something that we have to keep in mind when we tell people just how accurate these registrations should be in the real world. Okay. Now, luckily in the real world, most people know that they're not going to be very accurate. But I think it is important to keep emphasizing that this is a course registration tool. It's in fact something that I emphasize with people all the time when I show them the RUI. Or when I get asked, hey, how accurate does this have to be?
Very interesting. Thank you.
Thank you, Leah.
I got one more question.
Yes.
So we typically say it's 5 minutes to train and and 2 minutes to place, right? Is this still what we should tell them, or do we now have other numbers?
Well, I mean, there's stuff that goes into training for the RUI that goes beyond what we tested in the study, right? Like the whole thing about the metadata, the organ selection, the whole stage, of course, looks very different. I would say 5 minutes for training is a little ambitious, mostly because the tutorials that Bruce and I recorded are both longer than 5 minutes. But I think 1 minute per registration, like if you have a power user like Marta who has to register, 24 pieces, I could see that happen. Of course, then you also have to think about, it's not just the registration, they also have to download the file and properly upload it somewhere. And if you want to count that to the registration time as well, it's going to get a little bit higher. But I think as a goal, 5 minutes training, 1 minute of registration sounds those are nice numbers, and I think they convey the amount of time it takes pretty well.
Also, if you look at can you go to the slides of the plateau phase? Mm-hmm. The one before. So we see that that there's a median of about 8 tasks that are needed until a time plateau is reached for desktop users. And on the next slide, we see that this plateau has a median of roughly below 25 seconds. Okay. So once a plateau is reached, there is a very low time needed for the placement, lower than 2 minutes, even lower than 1 minute.
And that brings me to a really important point that I don't think we have really discussed yet in all that detail. So I'm going to go to a slide here where we actually see the RUI. So this is about moving the actual tissue slice. So what you see here, and I submitted this as a GitHub issue, and I think it's important. We can see that as we are here in register mode, so when the toggle switch is here on the left, our camera perspective shows depth. It's a perspective camera. So what that means is, once you go back to here, we actually perceive depth all across the kidney. In the RUI that we tested, when you're in the registration mode, you have an orthographic view, which is common for 3D modeling software, because you only modify 2 dimensions at a time. And you also only see 2 dimensions at a time. You don't see depth in this kind of isometric view. And I think that this makes the registration easier. And I think the current setup we have in the RUI version 1.0, we have 2 perspective cameras. So we see depth all the time. and that makes the alignment harder. So based on the data that we have, we could argue that having an orthographic camera is likely going to be superior to the rendering method that we have in there right now. That might also be a larger conversation we have to have, just like about, you know, making the rotation easier with handles instead of sliders, because that would be probably a major feature.
Yeah.
But this would be in support of the data that we collected, especially for, you know, registering many tissue slices or many tissue blocks at once.
And it's great to have Edward and others, Bruce and others from the programmer team here, so that they get to see that we don't just wing it, we actually try to bring science to all of this.
So Kadi, I'm going through the many questions that you posted, and I'm going to see what kind of answers we have for those. One of the questions was, is the completion time in seconds? The answer is yes. And then 447 seconds max. I'm trying to... That does not sound unrealistic. Some desktop users had a really hard time performing some of these tasks. I would not. This would be here probably. Yeah. Yeah. Some of the users had this issue where they were trying to be hyper precise and hyper accurate, even though, you know, their speed prompt, they might have gotten a speed prompt before. And then they just had all the patience in the world of fulfilling these, even though we know that there is no trade-off between completion time necessarily for the desktop condition. We know there is a full trade-off for the stand-up condition, where the longer you work on the task, the more precise you get. This trade-off does not exist for desktop. So maybe that's another thing that might serve as a design implication. Encourage people to not spend too much time on an individual registration, because they will not get any more accurate. That might be another important implication. All right, do we have more questions?
By when will the paper be written up? Some others might like to look at it after it's written up.
So December 17th is our absolute deadline for having the paper on archive or OSF, depending on what we decide on. Essentially, the paper is going to be uploaded there, just like the CCF paper is currently uploaded there. And it's going to be citable, it's going to have a DOI, and it's going to be readable. It's just not going to be peer-reviewed and published yet. But that's an important step. That's a milestone for HubMap. So that's like the latest date. We're currently working with high pressure on getting that paper out now that we already have this really nice data. I'm going to use the remaining 4 minutes to give you a glimpse into that second user study that we are also running as kind of a follow-up user study. Here we go. So we looked at all of this really pretty data that we got out of the HubMap, out of the RUI user study. And we thought it would be, there must be a way to allow people to optimize their performance through the use of data visualization. After all, data visualization is kind of what we do in our lab. So we came up with a modified user study design. This is the current user study design that we have. And in the modified user study, we would have two groups, a control and an experiment group. And the experiment group gets an additional piece called a reflective phase. And we would then compare the two plateau phase results with each other to see if there are significant improvements in one of the two groups. So again, control is basically what we talked about in this talk. And then we would have a new experiment phase data set where we would show users three-dimensional VR visualizations of their own performance in VR between these phases. And they would have different interactive methods of, for example, on the left side, skipping through the data set with this time slider. And here you see kind of the spatial layout. This is a visualization of the movement of one user together with the tissue block movement as well. We also have legends that are interactive. And the desktop at the same time would get, did get a line graph visualization of their distance and rotation and accuracy over time. And the findings were quite surprising to us, to put it that way. We found no difference for the two VR conditions. So the reflective phase that we designed did not yield significant differences in mean time, centroid inaccuracy, or rotation inaccuracy. However, it did for desktop. So the line graphs that we, the classic line graphs that we showed the desktop users who still, again, of course, worked on laptop, they actually achieved a highly significant lower rotation and accuracy. We can see that over here, and a slightly significant lower centroid inaccuracy. So the intervention that we designed worked for the desktop version, but it did not work for the VR version. So that prompted us to make some thoughts into how we can make those kind of reflective data visualization interventions more useful. And I'm quickly running out of time here, but these are some of the design implications that we got from just from analyzing the spatial data. So again, these two studies that we just talked about, they build upon each other. And yep, this is going to be the next paper we're going to be working on after the first RUI paper is out.
Great to see such a huge impact of the reflective phase for desktop. That's
we were really surprised by that. Yeah, we were really surprised by that, especially because for the rotation and accuracy, it becomes highly significant. So, and of course, we formulated a whole bullet point list of design implications for these kind of VR visualization interventions for optimizing performance and satisfaction. And we did find significant results there. We have a big correlation matrix that we couldn't put onto one slide between, you know, all sorts of spatial metrics like the space usage, etc., and then all of the performance metrics and accomplishment and satisfaction that come afterwards. And it is really interesting to see, like, for example, we identified some metrics that enhanced at least one accuracy measure later on. One of it was the total degrees of head rotation around the y-axis, so the amount of times that people looked around their own head, the total distance they traveled through the space, and the amount of the head moving up and down. So encouraging the 3D usage of space while being relatively stationary seems to be a good way of improving performances after these kinds of interventions. All right, we're at the end. Thanks so much, everybody, for attending our talk. In 2 weeks, we are going to we're going to see Ellen's and Leah's presentation about Seurat and Azimuth. And until then, I hope everybody has a good work week. And thanks so much, Kilian, for joining us at this late hour. It's been a pleasure. And
my pleasure.
Yeah. Everybody have a nice day.
Bye.
Bye-bye.